missed the morning. But where is it best that the speaker stands?
It doesn't matter.
It doesn't matter?
This is
Okay.
pretty wide range for
Okay.
the microphone.
Okay. Okay.
And if you want the pointer, you would have to use this one.
I'll just use the pen.
This one here, see laser, and then you can check.
Okay. I'll use the pen and then you can.
Okay.
Yeah. Or if you want to use it, you can do it. You
Okay.
can steer for the people.
All right.
Okay, so just go to the next slide, please. Thank you. Okay, so the eruption, can we hide the top panel?
Yes, if you go automatically.
Okay, cool. So it was a 6-month-long eruption. It started from the middle of March until the middle of September. It was the first volcanic eruption on the Reykjanes Peninsula in nearly 800 years. And it attracted about 300,000 visitors who went to go physically right up to the eruption. And so in this talk, I'm going to be talking specifically about the particulate pollution and the SO2 pollution that both residents in Iceland and visitors to the eruption experience. And we're focusing on SO2 and particulates because these are both associated with adverse health effects. In these pictures, so this picture here, this is one of the first days of the eruption. This is all of the people who were just rushing to go up and see the eruption. So you see it was a total traffic jam. And then over here is a picture of my oldest son. So whenever I wasn't working, I was going to the eruption with my family. So it was really something important and beautiful to experience. It was a effusive eruption. So almost everything that erupted was basaltic lava. There was very minor tufa erupted. It's relatively small. So the SO2 that was released was only about 6% of the SO2 released during Hólarain. Hólarain was a much larger effusive basaltic eruption that took place as part of the Bárðarbunga volcanic system between 2014 and 2015. And its lava was only about 10% of that which was erupted during Hólarain. However, because of its proximity to urban areas and the high number of visitors, there was likely much greater population exposure to the volcanic air pollution, even though it was a relatively small eruption. This is a map showing geographical clusters of the measurement stations we were using to measure the concentration of the particulate and SO2 pollution in the air. So the eruption site is here. So the eruption site stations will always be labeled G1, and then they're going up sequentially with how far away they are from the eruption site. So G2 is, so the sensors that were at G1 at the eruption site, these were uncalibrated, low-cost, portable sensors. So we don't know exactly what the values are that they measure. We use them to indicate high values of SO2. Then once we get to all the other geographical clusters, the instruments measurements there are made with research quality calibrated real instruments that are maintained by the Environmental and Power Agency. Is that your name in English now? I know. Yeah, okay. And formerly the Environmental Agency, but now Environmental and Power. And over here, we're showing the wind rose during the eruption. So this is the 6 months of the eruption, so that you can see that the most dominant wind direction during the 6 months was coming from the north directly out to sea. So heading out this way, so avoiding any of the places where people are living. And then the other most common wind directions were going straight up to the north, which was threatening Vogar, and then also heading this way towards the Keflavik airport. So this is a graphical display of what the different air quality sensors were measuring. So as we look at this, the SO2 is in the top left, and then the particulates are the other 3 squares. So most of the stations, both at the eruption site, and again, these are the low-cost portable stations, everything else are the high-quality reference stations. We're only measuring SO2 here. We're not measuring the particulates close to the eruption site. As we move further out to the communities on the Reykjanes Peninsula, again, it's only SO2. It's once we get to Reykjavik, the capital area, that we start to have sensors that are measuring particulates in addition to the SO2. And here we have the 2 stations which are measuring particulates in the PM1, PM2.5, and PM10, as well as SO2. Go to the next. Okay, this is a bit busy and difficult. We do need to see what's in the top of that picture.
How do we get out?
Okay, I'll keep talking while Pavla figures that out. As we look at this, in all of these, thank you. Okay, so the y-axis is the concentration measured SO2 in micrograms per meters cubed. On the y-axis, we're saying which station it was, and these are divided into the geographic clusters that I showed you before. So now we're only showing measurements from the reference station. So we're starting with Reykjanes, G2, and again, we're moving further away as we increase in number. And so what we're seeing here is that background is in blue and eruption period is in black. So we're looking at the SO2 concentrations. When it says no background, that is because these instruments were put out once the eruption started as an eruption response. So we didn't have background measurements there. Once we get to the Reykjavik capital area, we can see that the black points are going much, much higher than the blue points. So when we do the average over the entire time period, actually, it's quite low. So it's statistically significant. The time averaged SO2 concentrations in the air in Reykjavik during the eruption are significantly higher than in the background. However, the background is extremely low. Generally, the average SO2 background concentrations are less than 2 micrograms per meters cubed. That's the long-term average. The long-term average over the duration of the eruption in the Reykjavik capital area, it only goes up to between like 4 and 5 micrograms per meters cubed. So it's statistically significant, but it's still not very much. However, there's large increase in peak concentrations. So all of these whisker plots, all of the pluses are showing statistical outliers. So they're not outliers because we don't trust the measurements. They're statistical outliers because they're so different from the average. So what we're seeing is just that it's very easy to see that the eruption is increasing the SO2. On average, it's very small, but at peak times, it's a lot. On the right hand in orange, we have the number of exceedance events at each of the stations. So the exceedance level is 350 micrograms of SO2 per meters cubed. That's the black line. And then the orange stars are showing how many times that level was exceeded. So we have 2 stations on the Reykjanes Peninsula where these orange stars are above the orange line. So the orange line is at 24. The annual limit for SO2 threshold exceedances is 24 per year. And at 2 of our measurement stations, we exceeded this. Okay.
Oh, and oh, it doesn't.
Oh, no, it doesn't want to go forward.
Okay, maybe now.
Thank you. Yeah, okay, great. This is a short time window. This is 2 days in July. This is showing 3 stations from G3. G3 is the Reykjavik capital area. And here we have the SO2 hourly means. Here we have the time. And what I want to show you here is even though these stations are very near each other, the peaks and the concentrations of SO2 are quite offset. We have very fine differences in time and in place for the SO2. The volcanic plume is only being intermittently advected to the populated areas. So it's not very often like going and sitting there for a long time. It's very dependent on the local meteorology. And we're also finding that the edges of the plume are very distinct, very well defined. Stations that are very near each other, one might be detecting high levels of SO2 while the other is not. So this is what is driving the fine scale of variability.
And it does.
Yeah. Now we're going to move into the PM. As we look at this chart, PM10 is the top row, PM2.5 is the middle row, and PM1 is the bottom row. Again, background is in blue, eruption is in black, but now we have another color. We have red, that's for plume present days. We're defining plume present days as when SO2 is detected. So we're using SO2 as the tracer for when the plume is present. When we look at PM10 and PM2.5, what really jumps out at us is that the PM10 and PM2.5 that are being measured in the eruption period are not necessarily the same time when we believe the plume to be present. That means that the eruption is going on, but we don't think that the plume is actually present in the Reykjavik capital area. We think the wind took it somewhere else. Yet we're still having these peaks in PM10 and PM2.5. Most of these points, almost all of them, occur during 2 time windows when we had dust storms bringing dust into the Reykjavik capital area. So what this is showing us is that both dust storms and traffic had a bigger influence on the PM10 and the 2.5 than the eruption did. So these ash porphyry eruptions are not exceptional sources of PM10 and PM2.5 at these distances. However, When we go down to PM1, it's a completely different pattern and a different story. What we see here is that the PM1 for the plume present days is almost identical to the entire eruption. The PM1 is very highly correlated with the SO2. When the SO2 is present, the PM1 is present. And so what we find is that the PM1 is very clearly elevated during the eruption compared to the background. It is very plausible that volcanic fissure eruptions are the dominant source of PM1 in Iceland. Okay. When we look at the relative contribution of the different size spins of the particulate matter to the total PM10, so when we look at this, in the blue, we have background, in the yellows, we have the eruption, and in the oranges, we have the plume present. So again, this is when we're using SO2 as the tracer to say that the plume is there. The darkest color is always the contribution from the PM1. So we're looking at how much of the darkest color is PM1 in the three different regimes. And what we find is in the background, the PM1 contribution is between 16 and 24%. While during the eruption, it's between 24 to 32%. And when we go to the plume present, it's between 27 and 36%. So the PM1 to PM10 ratio is going up significantly due to the eruption. Okay, go to the next, please. So we're trying to fingerprint the different sources based on these measurements of the particulate matter size bins and the SO2. So just like we saw in the last slide, here we have volcanic plumes, here we have dust storms, and here we have background conditions. And what we see is that the volcanic plumes have the much higher PM1 to PM10 ratios. We had these two dust storms that I talked about during the 6 months of the eruption. We had 2 times when dust storms were bringing dust over the capital area. And what we find is that during the entire time of the dust storms, the PM1 to PM10 is quite low. And during the peak times of the dust storms, so when the dust storm was strongest, it's the lowest that we measure. The background conditions are intermediate. It is very important to point out that this is 2 dust events. Pavla has a paper where she looked at 2 dust storms in 2015, and she actually found a completely different PM1 to PM10 ratio for these 2 dust storms to what we observed here. What this is telling us is that we can't just say, okay, we know for sure now that this is the fingerprint of dust storms. We need to do more research. This isn't conclusive. This is just what we found during this time period. Here we've divided volcanic plumes into fresh and mature. Mature plumes, that's when we have what in Icelandic we call moða, or what in Hawaiian is called vog. That's when the SO2 has oxidized to form the sulfate particulates. And so this is characterized by a higher PM to SO2 ratio. So in order to have plume, you must have SO2 present above background. However, during mature plumes, the SO2 might be only a little tiny bit above background, but you're going to have still SO2 and PM1 present. And so that's why you see this. The mature plumes are fostered by low wind speeds, high humidity, and intense solar radiation. Those are the conditions when we have moða events in the capital area. And what we're saying is SO2 can be a proxy for PM1 at the stations where we measure SO2, but we're not measuring PM1. Okay. So when we try to think about what does this mean for the health of the people living in Iceland, so 71% of the national population lives within 50 kilometers of the eruption. So here's the eruption. Here's the capital area. So this is population, where the darker the color, the greater the number of people. It's also written as numbers. This is data that comes directly from municipalities, and this is the 2021 data. So of course, there's more people today than there was then. But what we see is there's high population density here, some high population density here. I'm going to go back to this windrows that we talked about earlier. So again, the most common wind direction was for going straight down. And then after that, it was going in this direction. And so we see that here we have the number of events where SO2 exceeds 350 micrograms per meters cubed. And here we have, so for each station, in parentheses, we have the number of SO2 exceedances. And also this is getting darker in color, the greater the number of exceedances. And so what we see here is at the low cost, uncalibrated sensors near the eruption site, we have lots of exceedances. So up to 1,400 here. Then when we go here, this is the community of Voga, and here we're up to 31. So this is the high population center that had the most SO2 exceedances was the community of Vogar. And so what is really important from this is that from a public health perspective, it was really fortunate that most of the volcanic pollutants were not being brought into the communities and were very rarely being brought in the direction of the capital area. So again, this is where most of the people live, and there were very few instances of SO2 exceedances. Okay. So we're interested in this because all areas that record above threshold pollutant concentrations might have experienced adverse health effects. So Fagerdalsfjall was very, very similar to Hollerein in terms of its impact on populated centers. So even though Fagerdalsfjall was 1/10 the size of Hollerein, the number of exceedances in Vogar was 31, with a maximum measured SO2 of 2,400 micrograms per meters cubed, while Hollerein, which is much, much further away, but was again 10 times bigger, there were 33 exceedances in Reykjavik of the SO2 air quality threshold, and the maximum was 1,400. So their impact on communities was very similar, despite the difference in size. So location really does matter. Okay, next, please. Now, when we think about the potential exposure of visitors to the eruption, so we have this visitor counting period, which is a little bit shorter than the eruption itself because it took a couple of days to start counting people. This works out to be an average of 1,600 visitors per day. And as I showed before, we had up to, it's actually 1,400, it's a typo, I'm sorry. We had up to 1,400 instances of elevated SO2 at the near eruption low-cost sensors. Can you go to the next one, please? Okay, so here we have, this is time. On the left axis, we have the percentage of hours with elevated SO2. These are the sensors that are near the eruption site. And then on the right axis, we have the daily number of visitors. So to be a 100% hours with elevated SO2, that would mean that for a full 24-hour period, the SO2 at that sensor was over 350 micrograms per meters cubed for the entire day. And so what we can see is that having many days in a row with very high SO2 at the sensors, this was not reducing the number of visitors coming to the eruption. But we were communicating about the gas hazard in many different ways. And one of the ways was that just advising visitors to remain upwind. Members of when the eruption first started, it was rescue team members, and as the eruption progressed, it became park rangers who were being at the eruption site holding handheld gas sensors to help advise the visitors, like if they were detecting SO2 at unhealthy levels, recommending them just move a little bit away. These local meteorological conditions mean that you could be an unhealthy SO2 here, but you could just make a smart choice. Walk over there, you'd be able to enjoy the eruption and not be breathing in high concentrations of SO2. And this was very effective. Very few people sought medical attention after visiting the eruption site due to gas exposure. And so this is a photo of one of our low-cost gas sensors. So you can see how low-tech it is. So thank you very much.
Very exciting talk. So I will just get back to Zoom here. So good, the sharing. And maybe ask first, many people are clapping online, but ask first, are there any questions for the SO2 expert of Iceland? Has anybody of you experienced ever this kind of be exposed to high CO2 level, SO2 level? Very irritating, so you would remember. Okay. So are there any questions? So it's nice that you are taking part in the workshop. Would you like to ask directly? Nice to see you. Hi.
Thank you. Thank you for the organization of this workshop. And thank you, Melissa, for your presentation. I was just wondering if you have done any comparison with satellite, with some assumption, I suppose, of the vertical extension of the volcanic plume above the station. It's probably complicated because the concentration of your sensor is probably too high to compare with satellite, but maybe you can mention some work on it.
Sure. So we've actually done quite a lot of work with the SO2 detecting sensors, like particularly trying to get out the SO2 flux from the eruption using the satellite images. So we have been part of studies both using IASI and various SO2 detection tools, Tropomi also. So the thing is that these eruptions, the plume height it can be high in the beginning of the eruption, but they tend to settle down to be right around the boundary layer height. So like our average plume height is about 1.4 kilometers. And so this means it's actually much easier for us to measure the SO2 from the ground using remote sensing techniques such as DOAS, rather than from satellites. It's actually really hard to detect these low emissions that are low to the ground using satellites. Also, it's very cloudy. We have like huge parts of the eruption. It's just, you can't see far at all. So of course, that also hinders how often the satellites are able to see the plume very well. So it's quite a challenging problem.
Okay,
Okay.
I would like to add here
Thank you.
because tomorrow we have a CAMS focus session. There will be one talk by Mark Barrington, and he will show the CAMS SO2 products, how they capture this event. So that might answer your question as well.
Yeah, when we have done detailed comparison with the SO2 fluxes that we measure from the ground versus from the satellite, the only thing that really agrees is like, where is the plume? The fluxes tend to not agree at all. Not well.
Okay, are there any more questions online? If not, thank you very much again, Melissa. Very happy to see this study because, yeah, this is one of other important sources of air pollution in Iceland. And the next speaker is Emma Gloria. Hopefully, I'm pronouncing that correctly. And she will talk about volcanic air pollution from Reykjanes eruption in Iceland again. And I believe it's starting your master or PhD project. So let me find the presentation. I make sure I'm sharing. Is it okay we will record it? We are still recording. And here. And the presentation mode. Do you want me to change the slides or not?
Hi, so I am a new PhD student a little about 4 months ago, so this is probably going to be a little bit more me introducing myself, talking to you a little bit about the work that I've done so far, and also just ideas for projects. Because I'm new, any advice or suggestions or ideas, very open. So yeah, so this is my background. It's a little bit all over the place, but I started out doing environmental science and focusing on marine biology. So I was looking at about a decade of data, analyzing fish and benthic communities to see how effective the sustainability policy had been. Then I didn't get into air quality, so I started my master's, which was the focus of my dissertation. And now I'm doing my PhD, which is I'm looking at lots of data again, but this time volcanic air pollution data. During my master's, I also started to do some work on a dementia research program. So I now have my original PhD was supposed to just look at transport, dispersion, and interactions with volcanic air pollutants, but now it might incorporate some health impacts, specifically about cognitive health later on. So my primary supervisor was actually Rachel, who Melissa just presented her work. She was also her primary supervisor, so my work's kind of following on from that. So the key findings, I won't go into too much detail, but again, pollution travels far. PM1 was a major source in Reykjavik, and also there's a lot of variability between stations. And since 2021, which is when Rachel's paper looked at, there has been 11 more eruptions, and also the air quality network in general has expanded quite a lot, so there's a whole lot more data to look at. So my first question was, considering this variability between stations, are there any stations that are frequently more exposed, like frequently have higher concentrations than others? So I wanted to see, specifically just started by looking at PM1. I am going to go on to look at the PM2.5, PM10, and SO2 later on. But I just want to start with PM1 because Rachel's paper was the first that gave a full reference grade time series during an eruption, so it's very understudied compared to the other pollutants. It also, Rachel's paper suggested that it's a major source of the volcanic eruptions. And on top of that, PM1 is a lot more potentially dangerous to the body because of how fine it is and how deep into the body it can get. For example, PM10, it usually stays around here in your upper respiratory region, whereas PM2.5 can get into your pulmonary and tracheobronchial region. PM1 can get into the deepest part of your lungs, and then from that it can get into the bloodstream, and eventually there's evidence that it can cross the blood-brain barrier and get into your brain, causing potential neurological impacts. So I defined the system of volcanic pollution episodes as where I surpassed the threshold for 3 hours. The reason I put it at 3 hours is because I wanted to look at multiple hour episodes where it just wasn't, where it was probably stagnating. I might end up changing it, but that's where I started. And because there's no currently internationally recognized PM1 threshold safe limit, I used the World Health Organization's PM2.5 limit for 24 hours. This one is for the most recent one, so it's a lot lower, but I also included the 2005 one just to do a comparison of the figures. So far I'm just looking at hourly data from the Icelandic Environment and Energy Agency and just covering the past 12 eruptions, including one in 2021. And I'm also just looking at the capital region for now. So there's 5 stations in the capital region that recorded PM1. And you can see here, basically what I did was I normalized it per eruption hours, and I turned it into 3-hour exposure blocks. So this is not total hours it was exceeded, but the frequency of 3-hour periods. These are the stations down here. So you can see the worst in terms of frequency was this one, and it also seems to be the worst in terms of intensity for Icelandic compared peaks, because the blue section is a lot bigger. And quite an important fact about this is that this one is directly outside of a kindergarten, so young people are probably more kind of pollution. These 4, they're in more open areas, but they're still in neighborhood areas. But this one is a particular concern. And then I looked at how they kind of distributed over the seasons. You can see in general that there's more eruptions here and here, but they do tend to form these longer persistent episodes in the summer. And then here I was looking at if they changed over the years. So you can see there seems to be a bit of an increase, but it doesn't seem to align with the eruption hours. I think an assumption that I made at first was that if the eruption was long, you would get more of these events. But if you look here, this is the longest eruption, over 4,000 hours. Whereas over here in 2025, it was only 514, but there's significantly more of these longer PM1 events in the capital region. So my next steps is that I need to make sure that they are of volcanic origin, which I'm going to basically follow the steps of Rachel, what she did, which is looking at SO2 and seeing if the SO2 is high, also looking at temporal patterns to see where you can see secondary aerosol formation. For all of those from the figures, they were defined during the volcanic period events, but I just need to go back when they're actually on volcanic origin. I'm also going to look at 10-minute data for those events to see if I can see where it might stagnate. I'm also going to look at meteorological data, and I might also, this is dependent on whether there is another eruption that tends to blow in that direction. We'll look at this mobile monitoring, which is basically creating a loop around one of these areas to see exactly where it's sticking. We kind of identify further who is getting exposed to the most PM1. When it comes to future chapters, it's really important for me to look at studies that don't only depend on there being another eruption. So this is one potential idea, which is looking at how pollutants are coming over to the UK using the UK's air quality samples network. You can see here they have SO2 has been recorded over the UK with some peaks in Edinburgh. that were higher than reported in Iceland in 2024. Other ideas, this is looking at, again, depending on whether there's an eruption and what impacts it has. But you can see here the smoke coming from where the lava is burning the roads, very different to the volcanic plume of the top. So the idea was to look at the composition and how it changes when it interacts with other environments. And here, pretty much the same theory, but it's more looking at how it interacts with wildfires that are ignited by the lava. And finally, I'm also interested in health research. So two ideas that I want to look at is more short-term impacts, neuroinflammation, cognitive function. A longer-term one is olfactory decline, which is the loss of sense, and the link with air pollution and neurodegeneration. But I would need some supervisors. So if anybody knows anybody who's in any of those fields or any referrals, appreciate it. Yeah, thank you.
It's so exciting to see the studies connected to the health because that's very important fact. Any question for Emma in the room? There's one. Maybe I will just bring you this because your phone.
Thanks for that great talk. When you showed the summer PM1 data, was that a lot of long-term data?
That was from 2021 to 2025.
So several years.
Yeah, so 12 eruptions and 12 years.
And like, I'm just wondering about the seasonal dependence, because of course volcanoes don't care about our seasons.
Yeah.
Is there any chance these are like small marine source aerosols, like freshly formed?
I think I don't know. That would be something I would have to look into. I was thinking it's potentially, I mean, when you look at 2025, they had some of the hottest summers on record for 2025. I was thinking there's probably a strong meteorological link and also a strong link, maybe wildfires if they're increasingly occurring. There were other things I was looking at, but I would also look at all that.
Thank you. So, any more questions here? Yeah. So I guess there are also no questions that there are no questions online, but I'm still sure that no.
Okay.
Thank you very much. And the next speaker is Turidor. Björk Winsdotter. I hope I have the correct pronunciation. And she will talk about the gap in the knowledge, and there is a massive gap. So I'm very happy that Turidor is going to ask. Turidor is also the representative of the ISDAS Association in the Nordic Society for Aerosol Research for Early Career Scientists. So the students, if they have more interest in aerosols and air pollution and impacts of aerosol, you can just talk to her. So I will find your presentation.
And I have been sick the last few days, so I apologize for my voice.
Oh, it's a really good microphone.
Okay.
You don't have, please don't push your voice, that's the worst. And I have, is it okay we were recorded, right? Yeah. Make sure we share. And share. Yes, sorry, yes. Thank you.
Yes, I'm Tirish, and today I want to talk to you about the chemical composition analysis of small aerosols. And I am doing a PhD at the Center for Chemistry of Clouds in Aarhus in Denmark. And my project focuses on the chemical analysis of secondary organic aerosols. So I focus more on like PM 2.5 or smaller and less so on dust, like many of you here. But being from Iceland, I have often wondered like what kind of studies and articles exist about the chemical composition of small aerosols in the Iceland air. And if there's anything similar to what I'm doing that I could maybe compare to. So I think it's interesting and exciting. So I took to the internet and tried to Google to find some interesting articles that might be relevant for me.
And I used search words such as these that contain Iceland and different ways of saying aerosol. And usually these give me pretty good results for relevant articles and exciting articles about what I'm looking for. But in this case, actually, most of them focused on dust, some inorganic content in precipitation after volcanic eruptions. And I actually found some articles on the effects of Icelandic eruptions on the chemical composition of small aerosols, but in other countries. So like Finland, Slovenia, or Lithuania. And I have actually not, as of now, found an article about small aerosol molecular level chemical composition in Iceland. Anything like exactly what I'm looking for and researching. And that actually kind of surprised me because small aerosols, they can impact the climate through radiation scattering and through cloud formation, and they are particularly significant for human health. And I also think that Iceland is a potentially very interesting setting for aerosol research because we have somewhat limited vegetation. We have a relatively pristine nature, strong ocean influence, and we have these volcanic eruptions. And there are a lot of studies about the chemical composition of small aerosols in mainly Europe and in North America, and also a decent amount in the Arctic and the Antarctic. But it seems to be quite limited here. So I would say that this is a gap in knowledge, and I think it would be very interesting to approach this gap to try to figure out what it's like in Iceland. So for my presentation today, I actually want to present two analytical methods that I and my group in Aarhus use to analyze some small aerosols, and I hope to kind of provide perspective and maybe some inspiration even for a potentially very interesting research subject. So the two analytes that these analytical methods focus on are, on one hand, microplastics, and on the other hand, secondary organic aerosols. So I will split my presentation kind of into two, where in each section I will talk about one of these analytes and the analytical method that I use for them, and show some application of this method and kind of try to put it into perspective for why I think it could be interesting in Iceland. Starting with atmospheric microplastics, they are defined as plastic particles with diameters of 5 millimeters or smaller. And when they have diameters of 1 micrometer or smaller, they are also known as nanoplastics, so very small. The first study on atmospheric microplastic was actually published in 2016. So this is a very novel topic. So there's actually quite limited knowledge on what their effects are on the climate and on. But there are some studies that do suggest that they can act as cloud condensation nuclei and as ice nucleating particles, and also that they have adverse health effects when inhaled. So this is important. But they are formed through the degradation of just bigger plastic products, which are all around us, through weathering or erosion, or by weakening by sunlight. And then the plastic particles are just suspended into the air through just general air disturbances around them. And they do fall back down to the ground, but if they're not removed, they will just be resuspended again and again. So this figure from Brownie et al. Illustrates very well, I think, the different sources of microplastic in the Western USA. And by far the largest source is road and braking emissions at 84%, but it is followed by sea spray at 11% and soil emission at 5%. And all of these, I think, are very prominent in the Iceland environment. Additionally, a possible source is long-range transport, which I think might be significant in Iceland, where the microplastics can be transported very long distances to remote and pristine environments. So for example, they have been detected in Svalbard, in the French Pyrenees Mountains, in the remote Alps, and I think even in the Arctic. So all this to say is, I think it's not unlikely that they can be detected in Iceland air. So the method that we have developed for analyzing airborne microplastics utilizes pyrolysis gas chromatography coupled to mass spectrometry. And really, really briefly, the sample is heated here in this pyrolysis module up to 800 degrees, which then breaks the polymer into smaller products that are characteristic of the polymer and are also more volatile. So they can come into the gas phase, where they can then be transported through this chromatography column where they get separated from each other. And then they're analyzed by the mass spectrometer. And in this way, we can get mass concentrations in the samples with with detection limits of below 1 nanogram to 25 nanograms for 7 different polymers that we developed a method for. And if you're interested in more details on the method, we have just published an article on it in the Journal of Applied Analytical Pyrolysis. But then I want to show kind of an example of the application of this method. And I have one day sample and one night sample from 2 locations in China. One of which is Xi'an, which is a megacity in mid-east China. And the other is Qinling, which is a mountainous area just outside the city. And I just want to emphasize that these are preliminary results, but I still think they're interesting to kind of illustrate my point. So here's what some of my results would look like, where the y-axis is the air concentration of the polymer, and the x-axis is just the different samples. So Xi'an during the day, during the night, and Qinling during the day and during the night for each of these. And we detected 5 polymers in these samples. So polypropylene, polyethylene, polyvinyl chloride, polyurethane, and polystyrene. And for all of the samples, the similar trend is seen that there's a higher concentration of microplastics during the day than during the night. And typically a higher concentration in Xi'an than in Qinling. And this, I think, is as expected because I expect both more production or more activity during the day. So I expect more production of microplastic and more resuspension during the day than during the night. And also more activity in the megacity Xi'an than in the mountainous area Qinling. Now, the polyurethane results are quite uncertain, but for the rest of them, we found between 20 nanograms per cubic meter up to 700 nanograms per cubic meter for polyethylene, which was the most significant polymer we found. But there was also quite a significant amount of polypropylene and polyvinyl chloride, I would say. But we did also find that a higher carbon content in the sample matrix would lead to a decrease in the signal of the analytes. And I expect actually a lot of that in the China samples. So theoretically, the concentration might be even higher. But I think the matrix in an Icelandic sample would be even cleaner. So the detection limit would be very low, I think. So I think this would be a very exciting study subject in Iceland. Yes, so that was one of the analytical methods. Now I'm going to move on to the other one, which focuses on secondary organic aerosols, or SOA. And just briefly about those, they are formed through gas phase reactions in the atmosphere, where the products can then condense to form particles which then impact the climate, like we know. The largest source for the gas phase precursors, which are known as volatile organic compounds, is vegetation, by far. And then the ocean is also a very large source. Sulfuric acid is also quite significant for new particle formation because it can act as the very seed of the particle, allowing the other compounds to condense onto it so it can grow. So Iceland has oceans, vegetation, and volcanic eruptions, which cover the basis for all of these 3 things. So I think it is quite a unique and interesting setting for looking into what particle formation is like in Iceland. I think it might be very different from, for example, the Arctic or Europe. So I think that's quite exciting. But the method we use, which is quite a typical method for SOA analysis, is liquid chromatography coupled to mass spectrometry, where you collect particles on filters, you extract them in a solvent, and then in liquid form, you can inject them into the LC, the liquid chromatographer, where it goes through the chromatography column. And again, the compounds are separated based on their hydrophilicity and then detected by the mass spectrometer. And we can quantify the concentration of known compounds. And if we don't know the compound, we can at least probe the structure of what that compound might look like. And we can get the relative abundances between samples, but then you can only compare the same compound to itself in other samples. But this is a very effective and very established method for SOA research. And again, I will have some examples for the application of this method, where first I'll show you some samples from the Arctic. So from northern Greenland, there's a research station called Billund. I have some samples from there that have been analyzed. And we have also analyzed samples from an icebreaker that went on a research expedition sailing through the Arctic Sea called the Art of Melt. And this is mostly just to illustrate my point. So I won't go into details of the analysis, but here are the chemical compositions from both sites. The top graph is the Art of Melt, the ship, and the bottom graph is Wilhelm Research Station, which is in Greenland. On the y-axis is the air concentration, on the x-axis is the day of the year. And each bar represents a sample that we analyzed, and each color in the bar represents a compound. So these 7 compounds I've included in the figure, those were the ones we found to be most significant in these samples. And of these 7 compounds, these 6 actually are biogenic in origin, so they come from nature, and likely from the ocean or from long-range transport from the continents. But there is also the top one, IPOX-OS, that is an organosulfate, and it is most likely from anthropogenic origin, so from human-made. And it's not a very big contributor, but it is seen here in particularly in the Art of Melt that's sent through the sea, but not so much in Wilhelm. But you can also clearly see that there is a difference in chemical composition between these 2 sites. But what if we now compare it to a totally different site, like Sian, the megacity from before? So for this one, it's the air concentration again, and then dates, where it's the 2 same dates, that's just day and night, so on. And immediately a difference you can probably notice is that the lowest concentration detected is 5 nanograms per cubic meter, whereas for the Arctic, the highest concentration detected was 0.6 nanograms per cubic meter. So there's way more particles in China. There's also 2 things that I want to highlight. There's way less pinic acid, for example, in this one than in these 2, and that's a very common product of biogenic origin. But there's also way more influence for MBTCA, it's called. And that's a more oxidized, more aged product. So again, there's a clear difference between these 2 sites. But now maybe you're wondering, which one does the Icelandic air composition look like? Because we have quite pure air and a lot of ocean influence, like here in the left samples, but we do have more exposed vegetation than the snow-covered and ice-covered green. Whereas we also have a lot of traffic and some industry, like they do in China. And then we also have our very own thing, which is the volcanic eruptions. So who's to say which one we will look like, what the chemical composition will look like here? So I think, again, that's why this needs to be studied, to really place it. So the messages I would like you to take with you today after this presentation is that there are actually several open questions on the chemical composition of Icelandic air, small aerosols at least. So, for example, is there any microplastic in Icelandic air? What exactly is the chemical composition of SOA in Iceland? Is it more like the Arctic? Is it more like Europe? Is it its very own thing? And how do volcanic eruptions actually affect new particle formation and the chemical composition of the particles in Iceland? That could be quite unique compared to other sites. So there is a gap in the network of knowledge that we have on chemical compositions of small aerosols throughout the globe in Iceland. Thank you.
Thank you for a very impressive presentation, and I hope we will meet you here in 10 years at our own department, researching all these important things that we have no idea. I'm actually surprised. Are there really no studies or microplastics?
None that I could find.
Yeah, nobody has ever looked at it. Don't you know at the environmental agency, no microplastics in the air?
We have very little information, I would say.
Yeah.
It was a very interesting lecture, and I think it's a new field in research of equality.
Yeah.
And there are maybe some condition here in the Reykjavik area where we use a lot of certain tires in the wintertime after the asphalt is just hard, and also microplastic from the tires. So it's very interesting.
Yeah, I think that's very interesting as well. Yeah.
Yeah, I think there were some short-term projects on the microplastics in Vatnajökull Glacier, and they found it. It is there. Ote probably knows better about it. So are there any questions for you? Yeah.
On the slide with the microplastics, there was one negative concentration, and I was wondering what that was.
Yeah, I think that's why I highlighted that these were preliminary results. Because this is results from when we were developing the method. So we hadn't perfected it yet. So but we decided to just try it on Chinese samples because if we're gonna detect microplastic anywhere, it's probably gonna be there. So I think for polyurethane, we used calibration curves and it was particularly bad for this one, the calibration curve. So I think it's just an issue with the calculation and the calibration curve. So I think we detect signals for polyurethane, but I cannot confidently quantify it. Yes.
So I thought it was so.
So
maybe this is Outi Meinander from FMI. Thanks for the great presentation and all the knowledge gap identifications. And I agree with Pavla that we will be excited to learn your findings after like 10 years or so and keep the how do you say in English, the interest on the topics because you brought up very significant questions. Yeah, I wanted to comment on the microplastics. I don't know about the atmospheric measurements, but like Pavla said, there are these microplastic analyses being made from glaciers in Iceland, and actually current research is being done at the very moment. So started like last year and ongoing now. And then I know there is a group of researchers who worked with the ocean topics, because there is one Icelandic professor who is part of the international society that sets the rules for what is considered microplastics, etc. I don't know or remember the name of the body, exactly what is the organization, but there is a high-level organization for microplastics in the world, and there is an Icelandic professor part of that group. So that's what I wanted to comment, and congrats for the great presentation.
Cool. Did you have a question? Yeah, just real quick. Did you say that we should think of sea spray as a source of microplastics?
Yes.
Thanks.
I think the reason for that is that the microplastic can get deposited on the surface of the ocean or into the ocean just through trash. And then sea spray and like breaking waves can eject them into the atmosphere. That is also just a big source of particles in general. So yes.
Any more questions in the room?
I will check online. Oh, there was really brave to ask me before. So are there any more questions online, please? If yes, please raise your hand and ask now, because we will proceed.
Yeah, I think they've actually.
Yeah, the glacier, Santiago.
I think they have suggested using microplastic as the start of a new era or something in when they're timing to a course.
Yeah, yeah. Okay, yes, thank you very much once again. I'll check on the schedule, so we are actually surprisingly on time. I'm so proud of it. That has never happened before. So at this moment, we would move from the, let's say, scientific based part of the workshop for the art part of workshop, which I'm very proud of. But I'm not sure. Do you think we shall take maybe first 5 minutes break and then start, because it was long, and then so we would start at the 15:40. I hope it's okay for everybody just to take a short break. So 15:40, we will start with the talk of the Emmanuel lesson, okay?